Okay, so today we're going to take a look at L'Hopital's rule. Okay, and this is the only section that we do from chapter 9. And then it can actually be applied to a lot of the limit problems that we saw way back in like chapters 2 and 3. So what we'll start off with is what is considered indeterminate form. Well, there are many types of indeterminate form, but the one of the two that we most commonly see are 0 over 0. The other one's going to be infinity over infinity. So if we want to evaluate a limit where the numerator and the denominator both go to 0, right? So if we look at substituting and we get 0 over 0, this is our indeterminate form. So L'Hopital's rule enables us to take the derivative and then evaluate the numerator and denominator again. So this is the first form. So if we take the limit as x approaches a of f of x over g of x, and when f of a and g of a equals 0, then we can do the derivative of the numerator and derivative of the denominator. This is not the same as the quotient rule. Okay, let's take a look at our first example. We have limit as x approaches 0. On a free response question, usually what they would like to see is that you show the limit of the numerator is 0. And if we take the limit of the denominator, we get to 0. I'm not going to make you show that each time, but when we do practice for free response questions, just get used to L'Hopital's rule, where you have to kind of show that first. All right, so I'd usually just put like an LH above. That shows my L'Hopital's rule. So I'm going to take the derivative of the top. That's going to be cosine x. Derivative of the bottom is 1. And now if I plug in, I get cosine of 0 is 1. So I get 1 over 1. Okay. This was actually one of the rules we did at the beginning of the year, and I had told you just to memorize it. But we can see with quick application of L'Hopital's rule, we can evaluate that also by hand. Okay, B, also, we could factor this, right? But for some problems where you have to factor, it actually might be easier to just apply L'Hopital's rule. So I'm going to do the derivative of the top. That gives us 1. Derivative of the bottom gives us 2x. Plug in 2, we get a fourth. Okay. Again, a just nice way to evaluate these, and no factoring is necessary. Okay, limit as x approaches 0 of tangent of x over sine of x. Okay, again, that would be 0 over 0. So we're going to do L'Hopital's rule. We do derivative of derivative of tangent is secant squared. Derivative of sine is cosine. We plug in 0 for secant. Well, that's going to be 1 over 1. Cosine of 0 is 1. So we get 1 here. Again, here we can see if we plugged in 1 with substitution, we would get 0 over 0. Again, these are problems that we did back in chapter 2 where I had you multiply by the conjugate, simplify it, but we're going to do L'Hopital's rule as an alternative. Derivative of the top is 1. Now, derivative of x squared, right? So that's going to be, this is x to the 1/2. So it's going to be 1/2 x to the negative 1/2, or 1 over 2 root x. Of course, we can take the reciprocal. Oops, that's a 1. We get 2 root x, and that results in 2. Okay. Sometimes we do the derivative of the top and the bottom, and we still end up with 0 over 0. So in that case, we have this stronger form, which just means we can repeat the process. So we're just going to keep doing derivative. So even if this doesn't work, we can do a limit again. Oops, that's supposed to be x approaches a. And we can do the second derivative, provided they exist, and so on. Okay. So let's take a look at example 2. Again, I can just do a quick check. If I plug in 0 to the top and the bottom, yes, I get 0 over 0. So I'm going to apply L'Hopital's rule. Okay, derivative of cosine is negative sign, so I'll make that a positive sign x over 2x. So when we try to substitute in 0, sine of 0 is 0. 2 times 0 in the denominator is 0. So we're going to repeat L'Hopital's rule. Here we get cosine x. In the denominator we get 2. Now we can evaluate this. We get 1 over 2. Okay, next one. We end up with 0 over 0. So again, I'm going to just do L'Hopital's rule. So we get 2x minus 4 over 3x squared minus 12. Of course, if we plug in the 2 to the numerator, we get 0. Plug in 2 to the denominator, we get 0. Repeat L'Hopital's rule. We get 2 over 6x. Plug in 2, and we get 1/6. Okay, let's take a look. Plug in 0 to the numerator and denominator. We can see that gives us 0 over 0. Evaluate the numerator derivative to x. Denominator is going to be e to the x minus 1. If we look and try to plug in 0, we get 0 over 0 again. So do the derivative of the top, we get 2. Derivative of the bottom, we get e to the x. Now we can evaluate. Well, we have 2 over e to the 0. Well, e to the 0 is 1. So we should just get 2 for that. Okay, we can also apply L'Hopital's rule to one-sided derivatives. Okay, as long as we still end up with that 0 over 0 indeterminate form. So here I want to apply x approaches 0 from the left. So I will have 4 cosine 4x, applying the chain rule. In the denominator, I get 2 cosine 2x. Plug in 0, we get 4 over 2, or 2. Here we have another limit, 0 over 0. Derivative of the numerator, secant squared x. Derivative of the denominator is 2x. Okay, now this is a different situation here. Basically, if I try to plug in 0 into the numerator, I get 1. But in the denominator, I'm going to get 0. So this is actually going to be undefined. This is no longer indeterminate form. So we can have a derivative where it's undefined, or we're going to write, instead of undefined, I should actually write does not exist. Okay, our other indeterminate form that we're going to look at in Calc AB is infinity over infinity. L'Hopital's rule applies just the same. In Calc BC or Calc 2, we look at a whole bunch of other indeterminate forms. We could have infinity minus infinity, 1 to the infinity power. Just remember that these are not real numbers. Infinity is not a real number. You can't find it on a number line. These are end behaviors of the graph when we're approaching positive and negative infinity. Okay, here we have x approaches infinity. Again, if we were going to do this on an FRQ, you would want to just show, right, this is going to go to infinity. The denominator also goes to infinity. So I'm going to apply L'Hopital's rule. Derivative. The derivative of natural log of x is 1 over x. Derivative of x squared is 2x. So if, I'm just going to rewrite this. Okay, so remember, like put that over 1. Let me just write it down here. Limit as x approaches infinity. That's going to become 1 over x times 1 over 2x, or 1 over 2x squared. As x approaches infinity, we get 0. Okay, so the next one we are going to look at as x approaches pi over 2 of 1 plus secant x over tangent x. And if you recall, secant and tangent both have vertical asymptotes at pi over 2, so they will be approaching positive infinity. So it's infinity over infinity. We have the derivative of the top is going to end up giving us, well, the 1 goes away and we get secant x tangent x. In the denominator, we have secant squared x. Okay, I am going to simplify this so I can cross off a secant and make that limit as x approaches pi over 2. Now I'm going to see if this simplifies. So I'm going to rewrite tangent. Well, tangent is sine of x over cosine x. And secant is 1 over cosine x. So I can rewrite this as cosine x over 1. The cosines will cancel, and now we evaluate as x approaches pi over 2 of sine x gives us 1. So that was kind of a combination of L'Hopital's rule plus, just rewriting it and using our trig identities. Okay, next one. We have limit as x approaches infinity of e to the x over root x. So the numerator is going to give us e to the x. The denominator, remember this is going to be 1 over 2 root x. If I rewrite this, I'll have e to the x times 2 root x. Well, as x approaches infinity, this goes to infinity / does not exist. Okay, the last one here. We apply L'Hopital's rule to the numerator, and that gives us 6. In the denominator, we get 2 to the x times natural log of 2. Now, when we evaluate this as x approaches infinity, we'll have 6 over something going to infinity, and that will give us 0.